So here we got a word problem because, of course, application of math is important to some people. So if a billiard ball is dropped from a height of 100 feet, its height s at time t is given by that function. And of course, you honestly should be able to write that function on your own because that's the classic physics equation. You got your acceleration times t squared. I guess that's not a naught because the acceleration is constant. So a, your acceleration times t squared plus your initial velocity times t plus your initial position. And so see how we got our acceleration due to gravity, because the acceleration due to gravity is like negative 32 feet per second-ish. And you got your initial velocity is 0 because it's just dropped, and from a height of 100 feet. So that's why this is plus 100. Except for I just realized I said that the acceleration was negative 32, and so it makes sense that it's negative 16. That's because it's a over 2. Right. So this makes much more sense. That's our physics equation. And so when we do this, we're actually not even going to be taking the derivative, right? Because they're asking us to find average velocity. So average velocity, that's the secant line. That's the slope between 2 points. So first off, we got to find these points. So let's say when x equals 1, so I'll write s of 1. Because see how it's like they didn't write s of x or s of t, but it's the s function, so I still think that's legit. So we'll say s of 1 is, what do you get when you plug in 1? What is the height after 1 second? Well, 1 squared is 1, so negative 16 plus 100. So 100 minus 16 is 84. So it's 84 feet at 1 second. And then, so recognize again, that's our point. That's the point 1 comma 84. But then what about at 2? What is s of 2? How high is it at 2? Well, negative 16 times 2 squared, so 4. So negative 16 times 4 plus 100. So what's negative 16 times 4? That's 64. So negative 64 plus 100. So 100 minus 64 is 36. So that's the other point, 2 comma 36. So what is the average velocity? Well, let's just find the slope between these 2 points. So let's do 84 minus 36 over 1 minus 2. So what's 84 minus 36? That's 48. So 48 over negative 1. So the velocity is negative 48 feet per second. Let's check that. 84 minus 36. Yeah, that's definitely 48. So negative 48 feet per second. Okay. So that's part A, from 1 to 2. Now we're looking from 1 to 1.5. So what is S of 1.5? So they might want us to use a calculator here, but I'm not down for that. So that's why fractions are nicer. So we're going to change. So 1.5 is 3 over 2. We should know this. So 16 times 3 over 2 squared plus 100. And see how that's way better, because how do you square a fraction? It's 3 squared over 2 squared, which means that this 2 squared can cancel with the 16 to make it negative 4 times 9 plus 100. That seems a little familiar, but it's actually the opposite, because now that's negative 36 plus 100, so we get 64. So at 1.5 seconds, let's do that, we get 64. And so what is the slope between those 2 points? You go the first point we have, so 84 minus 64 over 1 minus 1.5. So we end up with 20 over 0.5. And so 20 divided by 0.5, this actually reminds me of a math problem I saw people doing yesterday, where they were doing long division to do, I think it was like 4 divided by 0.5. And I was like, oh, that's so painful. First off, I don't believe in long division as a concept anyway. Second off, if you're dividing by 0.5, dividing by a half is multiplying by 2. So we don't need to do anything. We just need to do 20 times 2 and get 40. And there we go. There's our average velocity from 1 to 1.5. So next, let's do it from 1 to 1.1. So first off, we have to find s of 1.1. So let's see. That might be nicer to use a calculator, but I'm persistent, so I'm not going to. Plus, I can do 1.1 squared pretty easily because that's just 11 squared. And 11 squared is 121. So this is 16 times 1.21, which again is going to be better with a calculator, but I don't like calculators. And then plus 100. So what is 16 times 1.21? Well, 16 times 1 is 16. And then 16 times 0.2 is 16 divided by 5, which is 3.2. And then 16 times 0.01 is 0.16. And then plus 100. Did we drop the negatives? We dropped the negatives. All of that was negative. Negative, negative, negative. So what is that then? Negative 16 minus 3.2 is negative 19.2 minus 0.16. So we end up with negative 19.36. You know what? I feel like we should make sure that that's correct. So let's pull up numworks right quick. And because, we all make mistakes. So 1.1 times 1.1 times 16 is 19.36. Boom, 19.36. You'll love to see it. So negative 19.36 plus 100. We don't need a calculator to check that one. That is 80.64. Beautiful. But we're not done yet because now we have to find the slope. That's just the point. So now we got to find the slope. It's going to be 80.64. Let's see. Let's be consistent. So let's do 84 minus 80.64 over 1 minus 1.1, which I actually realized, let's step back real quick here, that's a negative 0.5, so that's a negative 40, which makes a lot more sense considering this was negative 48. This is going to be negative 40 feet per second. And then let's continue here. We have negative 0.1 on the bottom. On the top, 84 minus 80.64. So that's 3.36. Because if you have to write anything down, you should use a calculator. But you should be able to do 84 minus 80.64 in your head. You could even check it real quick to make sure it makes sense. 80 plus 0.64 plus 3.36. It does indeed get you 84. So you're happy on that. Right? Because it fills up, so it gets 81 plus 3. Yeah, so that's 84. So then 3.36 divided by negative 0.1, that's, well, remember, you're going to multiply by 10. You're going to move this decimal over. So you're going to get negative 33.6 feet per second. And so those are all the average velocities. Negative 48, negative 40, negative 33.6. And at first I was worried that was a big jump, but it's the same jump as the other one, so that makes sense. But what I wanted to do next is kind of see what it's getting at here, because you're doing from 1 to 2, and then you're doing from 1 to 1.5, and then you're doing from 1 to 1.1. So see how these keep getting smaller? It's kind of like they're getting closer and closer to some answer, to some specific number, to some specific velocity. So let's find the instantaneous velocity. Like we do calculus now. We don't need to find these average velocities. We can find the specific velocity at time equals 1. So let's go ahead and do that. Let's find the derivative. So s prime of t, since this is all in terms of t, is what? That's just the power rule. So also s prime. What is s prime? The derivative of the position is the velocity. I guess we should have said that from the beginning too. That you take, the derivative of the position is the velocity, because it's the rate and change of the position. The derivative of the velocity is the acceleration, because it's the rate of change of the velocity. How the velocity changes, which is what acceleration is. But we don't care about that here, we just care about the velocity. So what is the derivative? Well, power rule. So bring the 2 to the front, 16 times 2. negative 32. You see, that's our acceleration in the first place, times t, because you decrease the power by 1. And then the plus 100, that just goes away because the derivative of a constant is 0. And then now we can just plug in t equals 1. So we say, what is the velocity? The pencil almost made it. Made it 2 minutes after 9, but not to the end of the video. So watch this. The pencil was dead. We're going to plug it in like that. And then we're going to finish the video. Because that is all it'll take. Because we're almost done anyway. We found it was negative 48 from 1 to 2. It was negative 40 from 1 to 1.5. It was negative 33.6 from 1 to 1.1. And exactly at 1, v of 1 is negative 32 times 1. So negative 32. And you see how that works out. That it goes from 48. We look a little more specifically, 40. A little more specifically, 33.6. And then we go right on, and it's 32. So you see how it gets closer and closer to 32 as that time interval gets closer and closer to instantaneous. So that's a pretty cool example. We probably made that take way longer than it needed to, but that's part of the fun of it.